Hello and welcome to my presentation on the fire testing of grade 304 stainless steel plate material under transient state conditions. Nowadays, stainless steel is being considered as a potential alternative to conventional mild carbon steel for a wide variety of industrial, structural, and architectural applications. The reason is that stainless steel have significant advantages over mild steel in terms of appearance, corrosion resistance, durability, maintenance costs, recyclability, and finally, fire resistance. An improved fire resistance is specifically observed in austenitic stainless steels with a nickel-based structure. The most common type of austenitic stainless steel used worldwide is ASTM grade 304 and its equivalent grades, as you can see in the figure. The aim of this research is to study the in-fire mechanical response of this grade of stainless steel and to obtain mechanical models describing the behavior of the material at fire temperatures. The models are obtained with the aim of using for structural fire design purposes. In other words, we want to enrich the experimental database available in the literature for stainless steel plates under fire. When it comes to testing at elevated temperatures, we have two major approaches: steady-state test and transient-state test. Steady-state tests are more common and easier to perform, but as the tests are performed under constant temperature conditions, they cannot realistically simulate the real structural fire or the real building fire. So, for this purpose, transient state tests are preferred. They are infrequent because, compared to steady-state tests, they are infrequent because they need more complex test setup, and also the analysis of results is more difficult compared to steady-state tests. However, the results we can obtain from transient tests are more realistic for structural fire design applications. One of the complex aspects of the behavior of steels in general at fire temperatures is a phenomenon called thermal creep. Thermal creep is the time-dependent plastic deformation occurring in the material under load at elevated temperatures. For steel materials in general, the thermal creep starts to become significant when the temperature exceeds almost 35% of the absolute melting temperature of steel. And this temperature limit is usually exceeded in building fires. This means that to obtain a reliable model describing the behavior of material for structural fire design applications, our model should contain thermal creep strengths or thermal creep deformations as well. As to the methodology of this study, the transient state testing approach was used. In this method, the material sample is first loaded to the desired stress level, then while the stress is kept unchanged, the temperature is gradually increased with a constant rate until failure occurs in the material. And during the test, the total strain within the gauge length of the sample is measured using an extensometer. The total strain itself consists of three components: thermal expansion, time-independent strain, and also creep strain, which is time-dependent. The thermal expansion component itself can be obtained individually if a load-free test is performed using a transient approach. In this figure, you can see strain temperature curves in which thermal strain has been removed from the diagrams. Under 3 different stress levels, the test has been performed. And these diagrams can be converted into multilinear stress strain curves that are more familiar for designers and engineers. The procedure to convert strain temperature curves to stress strain diagrams is shown in the figure. As you can see, at any desired temperature, for example at temperature T2, a vertical line is drawn to cut the strain temperature diagrams, and then the obtained points that are stress strain pairs are plotted and connected together to form a multilinear stress strain curve at that specific temperature level. As you can see in the figures, the good point is that grip strains are implicitly included in these stress strain diagrams. In the present study, transient tests were performed under 14 different stress levels, and the heating rate used was 10 degrees per minute, which represents the median heating rate occurring in the building fires in steel structural members. Now that we have obtained the multilinear stress strain curves, they might be somewhat difficult to be utilized by designers and engineers because they prefer mathematical models. To this end, the modified compound Flamberg-Goskut model, which has already been developed for the behavior of stainless steel at elevated temperatures, was utilized and was fit to the multilinear stress strain curves. Here you can see the mathematical formulation of the model and the parameters. Some of the parameters are directly obtained from the multilinear curves, and some others can be obtained using regression analysis. As to the test setup, first the sample, the test specimen was cut from a 3 mm thick plate, and a subside specimen was used because imposing a uniform temperature distribution over the gauge length of a subside specimen is easier than a larger specimen. You can see 3 thermocouples attached to the gauge length of the sample, and the thermocouples are directly connected to the furnace controller, so that the temperature of the sample is directly controlled, and the specimen is mounted on the loading machine, and you can see the extensometer, which is attached to the sample to measure the strain. And here is the furnace, the split furnace, which is used to apply heat to the sample. Results. As previously mentioned, the thermal expansion of the material can be obtained if a transient test is performed under low-free conditions. In this figure, you can see the results of the present study for thermal expansion in comparison with the diagram presented in Annex C of Eurocode 312. As you can see, Eurocode significantly overestimates the thermal expansion of grade 3 or 4 stainless steel plates. It is on the safe side, but there is a kind of overestimation in Eurocode. And in the next figure, you can see strain temperature curves obtained at the 14 different stress levels. The stress levels, you can find the stress levels, the numbers shown on this diagram is the stress level in megapascal. As you can see here, we have some sudden jumps occurring in the strain temperature curves at the stress levels greater than 150 megapascal. The reason for these sudden jumps is because of the changes suddenly occur in the microstructure. Actually, the internal crystal structure of austenitic stainless steel slides and recombines when a significant amount of load and temperature is applied to the material, and as a result, we can see these jumps in the strength. This diagram, in this diagram, you can see the multilinear stress strain curves with broken lines and the modified compound Rambert discrete curves, two diagrams with solid lines at 9 different temperature levels up to 900 degrees Celsius. And the parameters of the model have been obtained and presented in the table. Now that we have obtained the material properties, we can discuss and compare the results of the present study with the data already available in the literature. First, elastic modulus, which is the slope of the stress strain curves at the origin. You can see here the results we have obtained for elastic modulus is markedly lower than the predictions by Eurocode diagram. In general, a significant disparity is observed between the results of the elastic modulus reported by different sources. This is due to the fact that measuring elastic modulus using stress strain curves is a very delicate experimental task, which is very prone to error. And we suggest that in the future studies, more accurate testing techniques such as the resonance technique method is utilized to gain more accurate and more reliable results for elastic modulus. As to the yield strength, as you can see here, a better agreement is observed between the results obtained from different studies, and Eurocode diagram seems to be on the safe side and can be utilized with good accuracy. Thank you very much for your attention. Thanks.